Welcome back. In today's video, we will be covering the basic concepts in electric circuits, the first of which is Ohm's law. Then we have short and open circuit, conductance. Some people pronounce this as Kirchhoff's or Kirchhoff's. So we have Kirchhoff's laws, which is KCL and KVL, and circuit topology. So KCL and KVL is the fundamental of which circuit analysis is based on. Circuit topology, the basic topologies, loops, branch, and nodes. So the first of these is Ohm's law. So Ohm's law states that, let's draw a resistor, states that the voltage V across a resistor is directly proportional to the current flowing through that resistor. So V is directly proportional to the current flowing through the resistor. And the resistance R is measured in ohms, and it denotes the element's ability to oppose the flow of electric current. So based on the proportional, we have that resistance is the constant of proportionality, which is R. So Ohm's law mathematically becomes V is equal to I times R. So for example, say we have a resistor with resistance of 5 kiloohms, which is R, and the voltage across that resistor is equal to 20 volts. We can find the current through the resistor by using Ohm's law. So that would be equal to V is equal to I times, well, we're going to manipulate that, and then we get I is equal to V over R. So we go ahead and we divide that 20 volts by that 5 kiloohms. We can just write that E to the 3 ohms, and that's going to equal to 4. We bring that E to the 3 up top, we get milli. So that would be milliampere. So the current through the resistor is 4 milliampere. So resistance can vary, and because it can, we can either have a resistance that fully opposes the current flow in a circuit, means that resistance is very high, or we can have no opposition to said current flow. Why? Let's take a look at why this occurs. So we already completed Ohm's law, which is the basic of which circuit analysis is built upon. We can then take a look at short circuit and open circuit, and this has to do with the resistance. So the resistance R can range from 0 to infinity. So R can goes from 0 to infinity. And an element with resistance R is called a short circuit. So, well, an element with resistor R equals to 0, the resistance equal to 0 is called a short circuit. So normally, a short circuit is a piece of wire. We have current flowing through, and we have voltage. However, the voltage is equal to 0. Why? We'll take a look at that. But first, let's discuss the open circuit. So for resistance at infinity, or real high resistance, the opposition to the current flow is very high, and therefore we normally call this open circuit, such as a switch. So current in this case, V in this case, so current is 0. The voltage across does not equals to 0. So in short, A short circuit is usually a connecting wire, as we just mentioned right here. And that wire is assumed to be a perfect conductor. So the opposition to current flow is non-existence. So when the resistance varies from 0 to infinity, Ohm's law then mathematically shows the short circuit and the open circuit. So let's take a look at that. So for R going to infinity, the quantity I is affected because we can't divide by 0. So what we're saying is, remember we have V is equal to I times R. And with resistors, with resistance, we have Ohm's law. We can look at voltage and we can look at I current. So if resistance is equal to 0, we know we can multiply by 0. So therefore, the voltage, if we multiply that by 0, the voltage is equal to 0. And if the voltage equal to 0, that constitutes a conductor. Current flows, but the voltage is equal to 0. However, if we take a look at when the resistance goes to infinity, we can then go ahead and take a look at this guy right here. We're going to see that I is now affected because we can't, if we take a look at I is V over R. We cannot divide by 0. So therefore, we look at this as when R goes to infinity. So when R goes to infinity, if we take the limit of R going to infinity, V over R then I then becomes 0. So if we say, for instance, if we divide a number by a really large number, this approaches 0. So basically, if it approaches 0, the current is 0, then we have an open circuit, which is that of the switch. However, the voltage does not equal to 0. So if we go ahead, cover it, Ohm's law, short circuit, and open circuit. Now conductance. As we mentioned, here we have a conductor. So conductance would be something useful to just mention. We don't have to solve any problems or anything for that. So conductance is a useful quantity. So let's just write down our equation for our resistor, or resistance, I should say. So conductance is a useful quantity in a circuit, and in circuit analysis, the conductance is the reciprocal of R, known as conductance. So, and that is denoted as capital G and is measured in Siemens. So if we reciprocate R, we then get I over V. Hence, this is then equal to G is equal to I over V. And the units for that is 1 Siemens is equal to 1 amperes per volt. So that's conductance. Next, I think we have the KCL and KVL, Kirchhoff's voltage and current law. So for these, we can then go ahead and just write down the current law first, KCL. So the algebraic sum of currents, let's just write that down first. So the algebraic sum of the currents entering a node or a closed boundary is equal to 0. So what that means is that if we have a node, let's say we have a node right here, 1, 2, 3, 4, 5. So I got 5 branches, and we have currents entering and leaving. let's make that one leave. So what if these currents is I of n? So that means we have I1, I2, I3, I4, I5. We can say this is 2 amps, 2 amps. This can be 2 amps, 3 amps, 3 amps. So N, so capital N, is the number of branches connected to the node being analyzed. So this node is being analyzed, and N in this case is equal to 5. I of N as the currents are the nth current leaving or entering the node, which is these guys right here. They're entering or leaving the node. So if we compute that algebraic sum, we then get, and by the way, a current entering the node is positive and a current leaving the node is negative. So then we get 2 amperes. So we're doing these current right here. 2 amperes plus 2 amperes. And then we plus a negative 3, which is this minus 3 amperes. Same thing for the other one, 3 ampere. And that should equal to 0. And we can see that equals 6, and 6 minus 6 is equal to 0. So the algebraic sum should equal to 0. And if you write that again, we see that N counting 5 I of N is equal to 0, which checks. So another thing to mention is that the sum of currents entering a node is equal to the sum of currents leaving the node. And that's why the algebraic sum is equal to 0. So we could actually go ahead and write that as move the negative 3 amperes and other negative 3 amperes over there. Negative positive 3, positive 3, 6 amperes equals 6 amperes. So the current entering the node is equal to the current leaving the node. So another one is Kirchhoff's voltage law, KVL. So we should just write that here. This is KCL. Oops. This one is KVL. And Kirchhoff voltage law states that the algebraic sum of voltage around a closed path or loop is equal to 0. So instead of using N, we're going to use capital M. So we're going to call that the mth voltage. So the algebraic sum, so the running is common M, and then we have capital M, V of M is equal to 0. So where capital M is the number of voltage in the loop or the number of branches in the loop, and V of M is the nth voltage. So KVL can be applied by taking either a clockwise or a counterclockwise trip around the loop being analyzed, and either way the algebraic sum of the voltage around the loop is 0. So let's draw a circuit. So say we have a resistor, a voltage source, another resistor, a voltage source, and another resistor. So let's call this V5, V4, V3, V2, and V1. So let's put our counterclockwise loop in red and our clockwise loop in black. So we can then go ahead and apply KVL and see how the mathematics relate to the statement. So if we write the polarity for the voltage as plus to minus, and those are chosen by us, so if we write those plus to minus, and plus to minus, we can then go ahead and write the expression for that. So the sum of voltages. So we can start by going around the loop in the clockwise direction. That will be written down in black. So we see a minus V1. So we in our case here, we encounter, so we're going this way. Here we encounter a minus sign, a plus sign, a minus sign. So a minus V1, a positive V2, positive V3, a minus V4, a positive V5. And that should equal to 0. So we can then state that the sum of voltage drop in a circuit is equal to the sum of voltage rises. What that means is voltage drops are negative, could be positive. It's the way the circuit is analyzed, but in a sense, negative. So we can then go ahead and say the voltage drop around the loop that we're studying is going to equal to, so we have V2, because the voltage drop is the drops across the resistors. So we have V2 plus that V3 plus that V5, and that is equal to the sum of voltage being supplied by the voltage sources. So as you can see, V4 correspond to the voltage sources V4, V1 correspond to the voltage source V1. These should be in capital. Again, we can go around in a counterclockwise. Go around counterclockwise, we can start from the voltage source V4. If we start from the voltage source V4, we get a positive V4, a negative V3, negative V2, and a positive V1, and a negative V5 equal to 0. We get ahead and we can manipulate this again. So V4 plus V1 is equal to V3 plus V2 minus V5. Well, that should be plus V5. So again, we see no matter how we analyze the circuit using KVL, we have to either choose counterclockwise or clockwise and stick with that throughout the analysis. So again, by doing that, we can see that the polarity of the voltages are chosen by us, the person analyzing the circuit, and not in the direction of the loop being applied. So not because we're going to apply, say after we apply counterclockwise, we're not supposed to just change the polarities just to analyze it in the counterclockwise direction or clockwise direction. Once we choose the polarities, we maintain those and then just analyze the circuit. So the next one is circuit topology, which is branches, nodes, and loops. And elements in electric circuits, can be interconnected in various ways. So understanding the basic network topology is important. Thus, let us look at like branches, nodes, and loops, which is these are just the basic topology of a circuit. So a branch, in our case, let's just draw one resistor. Let's just connect it like that. So a branch represents a single element, such as a voltage source or a resistor. In short, any two-terminal element. So here we have a two-terminal element, and it represents a branch. So a node. So a node is the point of connection between two or more branches, and at times indicated by a dot between connections. So in this case, we can then make this our node, which we can call our N1. So that's a node. Then we can then create loops. And if you wanted, you could go ahead and put another resistor there. So or another one here. So this now becomes a node. Here we have a branch, a branch, a branch. So now loops. So in any circuit, a closed path is constructed by starting from a node. So a closed path or a loop can be a closed path. So you start from a node, as in this one, and you travel around. You might enter another node, but you travel around a path to the same node. So basically what that means is that here have a loop, here we have a loop, and here we have a node. So that would be N2. So in this case, we can then say, let's use black and red. So let's start from N1 in red and just create a loop. So if we start at N1 and we go through N2 and end up back at N1, we have a loop. So this is basically a loop. So we start at N1 and end at N1. Another thing, or another one, is that we could start at N2 and we can go through N1 and end up back at N2. So that's also a loop. So here, you could also say we have loop 1 here, loop 2 here, and we have a loop, external loop or a larger loop. So 2 loops or 3 loops, depending on if you omit what's in the middle. So that's it for today's video. It's just a brief little overview of like some basic concepts that you need in circuit analysis. And in the next previous videos, I'll be going over like some problems and stuff like that. So tune in. All right, see you in the next one. Bye.